Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. This module discusses about handling of control hazards. So the objectives of this module are to discuss how to handle control hazards, differentiate between static and dynamic branch prediction, look at the concept of delayed branching, and all these are techniques for handling control hazards. The basically control hazards are caused by branches. Branches determine the flow of control for a program. So when you fetch the next instruction and if the next instruction is going to be dependent on a branch outcome, then you know that we are not going to have a sequential flow. So normally it is a sequential flow of instructions, but when you come across a branch, depending upon the outcome of the branch, the next instruction will have to be fetched from elsewhere, and because of that you have a problem, because in a pipeline, when the next instruction is being decoded, you also have the subsequent instruction being fetched from memory. So if you are going to fetch from the sequential address, then you have a problem. So that gives rise to what are called the penalties associated with your branch instructions, because the instruction is still working on the ID stage of the branch and it has not yet come out with the outcome of the branch. So whatever you fetched is going to be of a problem. So control hazards in the MIPS pipeline, how do we handle them? MIPS pipeline, if you look at the branch instruction in a MIPS pipeline, basically you know that we are only going to compare two registers. We are going to check whether these two registers contain the same value or not, and based on that we are going to do a branch. So this comparison normally happens with the register operands in the ALU execution stage, which is the third stage of your MIPS pipeline. And depending upon the comparison being true or false, you calculate the target address by adding the displacement to the current contents of the program counter. So this is normally done at the execution stage, and because the execution stage happens in the third stage, is the third stage of your pipeline, and your PC gets updated because of that, you have a 3 clock cycle penalty that you will have to pay whenever you come across a branch instruction. So if you have to reduce the penalty associated with your branches, then you will have to shift these operations of comparison of registers and calculating the target address a little earlier in your pipeline. So you can probably shift it to the ID stage. So if it is shifted to the ID stage, then you can reduce the penalty associated with your branch instructions. So we basically talk about what is called a control dependence. Just like how you have data dependencies and they will give rise to data hazards, you have a control dependence, and because of that control dependence it will give rise to what are called control hazards. Let us assume you have a piece of code like this. Some condition P1 is being tested for, and based on that you have a segment S1 getting executed, and then you have a condition P2 being tested for, and based on that you have another segment S2 getting executed. Now you know that S1 is dependent on P1 and S2 is dependent on P2. Now the problem is your control dependence. An instruction that is control dependent on a branch condition cannot be moved out of the branch so that it is no longer dependent on the branch. You can't do that. Similarly, an instruction which is outside of the branch and not control dependent on the branch, you cannot bring it inside the purview of the branch so that it is controlled by the branch. So these two properties will have to be adhered to, and if you violate these properties, that will give rise to control hazards. And basically when you are talking about control dependence, there are two major issues that you will have to address and take care of when you are talking about control dependence. One is exception behavior and handling, and the second one is data flow. Now what do you mean by exception behavior and handling? So whenever you have an exception, what you talk about preserving exception behavior is any changes in the instruction execution order. See, branches basically change the flow of instructions. It will change your control flow. So when you try to change the control flow and try to change the order in which these instructions get executed, it should be able to preserve your exception generation. That is, because you rearrange your instructions and reorder them, new exceptions should not be generated. This is a major issue which will have to be handled. That is what is meant by exception behavior and handling. The second one is a data flow, because when you talk about branches, there is a certain flow of data that occurs between these instructions, and depending on whether a branch is taken or not, you may go to a different address, you may execute a different set of instructions. Accordingly, the data flow changes. So, this data flow will have to be preserved. So, both the data flow will have to be preserved and the exception behavior will have to be preserved. So, getting a little more detail into these issues, look at an example here for exception behavior. So, I have an instruction here which says branch on equal to z R2, check R2 for being equal to 0 or not, and if that condition is satisfied, you will have to branch to an label L1. If that condition is not satisfied, that is if R2 does not contain a value of 0, then you will have to execute the load instruction which loads data from 0 R2 address into register R1. Now, the way this snippet has been written is the branch on equal to z instruction is a guarding branch there. So, suppose if R2 contains a value of 0, you are not supposed to execute the load instruction here. You are supposed to skip that and go to label L1. If you try to move the load instruction ahead of the branch without giving importance for that branch, if you try to reorder it for some reason, what will happen is the load instruction may get executed, and the load instruction will cause a problem if register R2 has a value of 0. So, because you know the load is going to happen from 0 R2, and if R2 contains a value of 0, it is going to try to attempt to load data from memory address 0, which will give rise to a memory protection violation. So, this is a typical problem of control dependence which will have to be handled. So, you can't just shift the load instruction ahead of the branch, and because of that land up into memory protection violation. So, this exception, otherwise it would not have got generated. If you had executed in the proper flow, this exception would not have generated. Just because you are trying to move it to a different location, you can't raise this exception unnecessarily. Similarly, when you are looking at data flow basically gives you the actual flow of data values among instructions that produce results and those that consume them. So, some instructions generate the results, with certain instructions use those results afterwards. And when you have a branch coming in, you know that the data flow is going to get altered. So, because of your reordering of instructions, you should not affect the way the data flows. So, branches make these data flow dynamic, and they determine which instruction is the supplier of data. You cannot violate that data flow. Say for example, I have an example here. So, you have a DAD instruction which modifies R1, you have a sub instruction which modifies the register R1. Now, when you are executing an OR instruction, you are using the value of R1. Now, whether this OR instruction will use the data that is generated by your ADD instruction or it will use the data of your sub instruction will depend upon the branch getting executed. So, you can't move these instructions such a way that the data flow gets affected. So, you will have to decide whether OR is going to depend on the ADD instruction or OR is going to depend on the sub instruction. That basically depends upon the branch instruction getting executed and the branch condition being evaluating to be true or not. So, this data flow has to be preserved. So, these are the two main issues that you will have to look at when you are looking at control dependencies. The data flow will have to be preserved and the exception behavior will have to be preserved. So, we look at a control hazard example here. So, the first instruction is a branch instruction here which compares the registers R1 and R3 and shifts control to a label 36. 36 is some XOR instruction given here. So, the branch shifts control to label 36. Now, if you look at the pipeline implementation here, by the time the branch instruction gets resolved in the sense the condition gets evaluated and the branch target address gets calculated, because you know a branch can be resolved only after the condition has been evaluated, and if you find that the condition is true, you will also have to change the branch target address. So, only when both these have been done, you say that the branch is resolved. So, by the time the branch has been resolved, which happens in the third stage, the ALU execution stage is where you do the comparison and you calculate the target address. and it is only during the fourth stage that the PC actually gets updated. Now, by then you already fetched all these instructions. You already fetched the AND instruction, you already fetched the OR instruction, and you already fetched the add instruction, and they have also moved on to the other stages. So, now you have a problem. Suppose if you have already fetched and started going decoding and all that for the subsequent instructions, and later on you find out that it should not be an AND instruction that will have to be fetched, but it is an XOR, you have a problem, and that is what has been given. So, only after the branch has been evaluated, you know for sure that this is the next instruction to be fetched and executed. So, that is an example of a control hazard. So, now what happens if you have this problem? If can we just ignore it? You can't ignore your branch problems because they are very, very frequent in your code. We normally say about 30% of your instructions are branch instructions, and the example that we saw here, we found that it has a stall of 3 cycles. So, when you have 30% of your instructions being branch instructions, and every one of these branches is going to cause a stall of 3 cycles, then the penalty that is caused is going to be very, very high, and it is going to bring down a huge dip in performance. So, this is obviously not acceptable. So, how do we handle this? So, a fundamental rule is you will always have to evaluate the branch condition early, and you will also have to evaluate the branch target address earlier, because unless you know the branch condition and you also calculated the branch target address, you cannot resolve the branch. So, if you are able to do these earlier, then you are going to try to reduce the penalty associated with your branch. And in the case of your MIPS architecture, you only test whether the register contains a value of 0 or not. So, the solution that you can provide for your MIPS architecture is either comparing two registers and finding out whether they have the same value, or checking for a register containing a value of 0 or not. If you can do this comparison during the second clock cycle itself, the first stage is wherein you fetch the instruction, the second stage is wherein you decode your instruction and you also read the registers. So, when you read the registers itself, if you are able to compare the register contents and if you are able to evaluate whether they are equal or a register contains 0, that is shifting the 0 test to your ID stage, then that gets done there itself. And the target address calculation is just adding whatever displacement is given in your instruction to the current contents of the program counter, which is PC plus 4 now. So, that can also be done during the second clock cycle itself. So, if you are able to do all that, then you know you can reduce the number of clock cycle penalty that you will have to pay. So, in order to do that, this comparison will have to be done in the IF stage, and you will also have to bring in a new adder. You can't rely on the ALU to do this anymore. So, you will have to introduce another adder in your decode stage, decode and read operand stage, and this adder will do the target address calculation. Now, if you do this, then you have reduced your penalty from 3 clock cycles to 1 clock cycle. So, what are the various, having discussed what the problem is and how it can be handled in a MIPS architecture, we look at all the other general solutions. Now, the general solutions that are provided for your branch hazards are, the first solution is the simplest of solution, but obviously not a very effective solution. Stall until the branch direction is clear. You do not take any action, you wait till the branch direction is clear, you decide whether the branch is going to take or not, and after that you perform the fetch again. So, once you know for sure that the branch is going to take or the branch is not going to take, then fetch from the target address or fetch from the subsequent address. The second one is, instead of just remaining idle and waiting for the branch to get resolved, you can go ahead and predict the outcome of branches. After all, there are only two outcomes. The branch is either going to take or the branch is not going to take. So, you can do a prediction of the outcome of branches, and based on the prediction, you can start fetching the next instruction. If your prediction is correct, you do not have to pay the penalty. If your prediction is wrong, you will have to pay the penalty. And branch prediction, so, is the ability to make an educated guess about the way a branch will go, whether the branch will be taken or not. So, what about the first option? So, if you look at the first option, where you either stall the pipeline till the branch gets resolved, or every time you have a branch coming in, you do the instruction fetch again, irrespective of whether the branch takes or not. You are going to take a major hit in performance, because this happens whether the branch is taken or not. But this guarantees that the PC will always get the correct value. But you know, this is not a very effective solution, because you are not really utilizing the fact that you could have gone right, and hence you need not have to pay any penalty. Because in any case, you are not going to take any action, and you are going to wait, and you are going to perform the fetch again once the branch is resolved. So that really is not going to give you a very good performance improvement. So for example, here I have the first instruction, I have the second instruction, I have identified that it is a branch. Once you know that it is a branch, once the branch has got resolved, go ahead and fetch the instruction again, irrespective of whether the branch takes or not. So the intermediate clock cycles, you have really not done any useful work here. So this method will work fine, but as always in computer architecture, we are violating the basic thumb rule of make common operation fast and effective. One of the major most important thumb rules in computer architecture is make the common cases fast. Now branches are really going to be common cases, because 30% of your instructions are branches, but still we are not making it fast and efficient. So that violates the basic principle of computer architecture. So by performing if twice, we incur a performance loss of about 10 to 30%, which is definitely not acceptable. So we will have to look at other solutions. Stall on branch. Similarly, if you look at stall on branch also, you are basically waiting till the branch outcome is known. So once the branch outcome is known, you idle till then, and only then you go ahead and fetch the next instruction. This again is not a solution, effective solution at all. So this has been given here. So once your branch is resolved, even if you assume that the branch gets resolved in the second clock cycle, so the second clock cycle you don't have to do anything. You stall, and then once you, so a bubble is created there, so you're stalling there, and once the branch has been resolved, then you go ahead and fetch the subsequent instruction. So that is the effect of either performing if twice or waiting till the branch outcome is known. Both these are not effective solutions. So we look at other solutions for your control hazards. So a very effective solution is doing a branch prediction. So as I already pointed out, the branch has only two outcomes. The branch can either take, or the branch will not take. So you can always make an educated guess of whether the branch is going to take at this instance, or the branch is not going to take. So you will have to predict both the branch condition, because two things will have to be evaluated for a branch. The branch condition will have to be evaluated, and the branch target address will have to be evaluated. So you make a prediction about the branch condition, you make a prediction about the branch target. And remember, these predictions are made even before the branch is decoded. That basically happens when you are looking at predicting the branch target, the details of which we will discuss as we proceed. And you may also look at other optimizations where you not only prefetch from the predicted address, you prefetch and execute from the branch target address even before the branch is resolved, which is called a speculative execution, which again we will discuss in detail as we proceed. So when you look at these solutions, the first solution is you are predicting the branch condition. So when you are predicting the branch condition or the path prediction, this is obviously only for conditional branches. Unconditional branches, you don't have to check for any condition, so there is no prediction about these conditions. And you have a branch predictor which will predict the outcome of the branch. And there are basically two types of branch predictors, or a static predictor, and you have a dynamic predictor. A static predictor is one where the actions taken during a branch do not change, they are static, and it is done by the compiler at compile time. So it does not get changed. So if it has to be changed, it will have to be recompiled with other conditions. But when you look at dynamic prediction, depending upon the behavior or performance of your branch prediction, it will keep changing at runtime. So based on the execution history. So that is the difference between a static prediction and dynamic prediction. So we look into details of the static prediction techniques in this module. Similarly, when you are looking at branch target prediction, you will have to predict the branch target address. So, for that you make use of what is called a branch target buffer or a target address cache, a TAC or a BTB as it is called. And this stores the target address for each and every branch, and it is accessed with the current contents of the program counter. And you obviously do not store the fall through address, because for a fall through case it is only the sequential address that you need, you do not need the target address. And this can be combined with a branch condition prediction, but separate branch prediction table is more accurate and is more common in recent processors. Again, the branch target prediction we will discuss in detail as we proceed. So, first of all we look at static prediction. Before that, just to look at other solutions, you look at what is called a return stack buffer. So, it is not just that you will have to store your return addresses for your normal branch instructions. Many times you have a branch instruction caused by means of your subroutine calls. You have function calls, and because of that you have control being transferred to a different place, and you may have to return from the function call to your main program. So, in order to handle this, additionally you have what is called a return stack buffer, which is implemented in a processor. This stores the return address or the fall through address for procedure calls. And basically what happens is, whenever you make a procedure call, it pushes the return address onto the stack, and when you return from the procedure call to the main program, it pops the return address from the stack. So, we will get into details of static prediction. So, as I pointed out earlier, static prediction is basically done by the compiler. It is based on the typical branch behavior. For example, loop and if statement branches. So, you know that iterative loops, if a loop has to be executed n times, the loop is going to be executed n times anyway. So, it is very easy for the compiler to make a prediction about these branches. So, you normally the compiler predicts that backward branches will be taken and forward going branches will, it is normally to exit the branch, so will not be taken. So, you can make use of this profile information of your programs or general information about the behavior of the branches, and based on that the compiler can do a static prediction. So, here because the prediction can either be a taken prediction or a not taken prediction, you have two options. So, a predict not taken approach, you assume that the branch is not taken, that is the condition will not evaluate to be true. So, in this case you assume that it is only the sequential address which you will have to use, which is very easy to handle. Now, a predict taken approach is wherein you assume that the condition is going to be evaluated to be true, and you will have to fetch from the target address. Now, in both cases, because you are talking about a static prediction here, so suppose at runtime the actual execution goes against the static prediction that the compiler does, you cannot execute wrong code. So, basically what happens is, the most probable path is taken and the most optimized path will be the most probable path depending on what prediction the compiler does. So, suppose if the compiler has predicted that the branch is not going to be taken, the most optimal execution you will get when you are going through that not taken path. But still, even if you assume the taken path at execution time, at runtime, you should make note of the fact that you cannot give wrong execution. So, basically you will have to write compensatory code. So, you may have to execute certain instructions again, but the execution will not be faulty, but you may take more time for execution. So, that is the basic concept for both the predict not taken approach as well as the taken approach. The third method that we look at is delayed branching. Delayed branching is a very effective technique. So, if you look at the predict not taken approach, so you assume that every branch is not taken. So, you simply take PC plus 4 and start fetching the next instruction from there. At execution time, if it gets wrong, then you have the compensatory code which will anyway compensate for that and get the wrong execution. So, if there something goes wrong, you will have to clear the pipeline and you have to load it from the not taken path. Predict taken approach is just the other way around. You assume that the branch is taken. So, will work for processors that have the target address computed in time for the if stage of the next instruction, so that there is no delay and the condition alone may not be evaluated. You still do not know the condition, but the target address is known for you. So, you can go ahead with the predict taken approach. So, does this work for a 5-stage pipeline? Or a 5-stage pipeline, the branch address, if you recall the MIPS architecture, the branch target address and the condition evaluation both happen during the either the third clock cycle or the second clock cycle if you want to reduce the branch penalty. So, it is not possible to go in for a predict taken approach here. So, if you look at the static prediction, these are some results which show you the misprediction rate. If the compiler assume that the branch is always taken, where you find that the misprediction is even takes on very high values. The second case is where it makes a more judicious choice of assuming that the branches take if it's a backward branch and branches don't take if it's a forward branch. You find that the misprediction has really come down. Now, the next technique that we are going to look at, which is very effective, is delayed branching. Delayed branching is a better approach, and basically what we try to do here is you pick up an instruction. In simplest terms, you pick up an instruction which is outside of the branch. It's a very useful instruction in the sense that it will anyway have to be executed, and put it in the branch delay slot. So, once this instruction goes into the branch delay slot, it will anyway get executed by the processor. And instead of executing some instruction which is not needed, you try to put in a useful instruction so that irrespective of the outcome of the branch, this instruction will get executed. That is the concept of delayed branching. But it is easier for the compiler if there are less number of delayed slots. If you just have one delayed slot, then it is easier for the compiler to identify a useful instruction. As the slots increase, the compiler may not be able to fill up the branch delay slots. Now, there are 3 different ways of introducing branch delay slots. What you mean by branch delay slots is the slots following your branch instruction which are a little ambiguous. You do not know whether these instructions will have to be executed or not. Those are called branch delay slots. So, the one delay slot allows proper decision making and branch target address in your 5-stage MIPS pipeline. Increase in the number of branch delay slot makes it very difficult for the compiler to find useful instructions. So, if you look at the 3 options from where you can fill instructions from, one is filling before, that is independent instructions. The other one is from the target address itself, and the other one is from the fall through path. So, this gives you an idea of what happens here. So, if you are sure of identifying an independent instruction not related to the branch at all, take that independent instruction and put it into the branch delay slot, which will anyway get executed by the processor. This is the most effective solution. But if you are not able to do that, then you will have to look at picking up from the target path or from the fall through path. Now, again you will have to be a little cautious here, because you know that when will you pick up from the target path? Only when the compiler predicts it to be taken. Similarly, you will pick up from the fall through path when the compiler predicts it to be not taken. So, if your prediction is correct, you can pick them up, but again remember that you will have to write compensatory code, so that if there is any problem, you will be able to handle these issues appropriately. So, limitations on delayed branching technique is dependent on the number of instructions. So, you have a restriction on the number of instructions scheduled in the delayed slot and the ability to predict if at compile time whether the branch is to be taken or not. So, if you are not able to identify such instructions, you may have to simply fill it up with no op instructions, which are not useful instructions. So, you are not really going to get any improvement in performance. And also remember that if you are going to use delayed branching, additional PC values are needed in order to allow safe operation in case an interrupt happens. So, this is an example showing how you can evaluate the branch alternatives. You know, the pipeline speedup is always given by pipeline depth divided by 1 plus pipeline stall CPI, where 1 is your ideal CPI value, and because of control hazard you can have stall cycles, which is defined by your branch frequency into your branch penalty. So, this is an example problem that has been worked out. You can just go through this problem, and depending upon the various branch alternatives, the alternatives that we have studied, whether you are looking at stalling option or you are looking at the branch taken option, the not taken option or the delayed branching option, you find that the delayed branching option gives you a better value of speed up. So, delayed branching downside is it is difficult to find instructions, And particularly when you are looking at a deep pipeline with 7 or 8 pipeline stages, multiple instructions issued per clock in a superscalar and all that, it becomes very difficult to fill up the branch delays. This is again an example problem which has been worked out. Just look at these solutions. This is another example problem that we have looked at. I have given you the solution. This is again an example problem. So, to summarize, control hazards basically arise due to control dependencies caused by branches, and you can't really ignore them because branches are very frequent and they will have to be handled appropriately. So, there are different methods available to handle control hazards. We have just looked at some of these methods. We have just focused on the static prediction methods. So, you can either stall the pipeline till the branch is resolved, or look at static prediction of either a taken approach or a not taken approach, and finally we looked at what is called the delayed branching. Thank you.